Okay, this is sort of a higher level concept than what we looked at before. This is determining the electric field from the electric potential. It has to do with actually two-dimensional, well, actually you can go all the way to three-dimensional, but it has to do with vector calculus. So this is a little bit advanced. It deals with a function we call a gradient. But you know, it's almost worthwhile to visualize this in terms of our analogy that we used before, in terms of gravity and the idea of a hill. So this is the ugliness. If we have the electric potential going by this equation right here, the integral of E dot ds, where ds represents an infinitesimal movement on a path length, then we can take the derivative of both sides, get dv is equal to E dot ds. Again, if you haven't had some of this vector calculus, this is going to seem a little bit mysterious to you. But we can think of the infinitesimal electric potential here as being the dot product of E dot ds. There's Ex dx plus Ey dy plus Ez dz. Remember the dot product, you take the product of the x components plus the product of the y components plus the product of the z components. That's where that comes from. Okay? And now we sort of turn this around a little bit using partial derivatives, and we turn it on its head and say, well, then Ex becomes the derivative of the electric potential, partial derivative with respect to x. Ey becomes the partial derivative with respect to dy. Ez becomes the partial derivative of v with respect to z. Your head's probably turning pretty good right now. Okay, putting it all together, that says that the electric field is therefore the partial derivative of the potential in the x direction times the I vector, the I unit vector, the partial derivative of the potential, that should be dy by the way, times the j direction. Dv dx should be dz, by the way. I'll change that and make that correction in the k direction. And if you have done some vector calculus and you actually have the proper variables here, you'll recognize this to mean that the electric field is equal to what is known as the gradient of the potential. All right, what does this mean? Well, it basically means that if you could imagine a topographic map, okay? And basically, the steepness of a hill on that topographical map was represented by some vector, pointing downhill. For this electric potential, if we graph that like a topographical map, that steepness of the slope would be related to the electric field, meaning that how quickly the potential drops off would be related to the electric field. And what this tells us is that our electric fields are stronger when the potential is going down faster, okay? And the electric field is weaker when the potential is not dropping off as fast. So, again, it's always easier to sort of visualize this. And again, we're throwing around a lot of fancy, notation here, but we can think of a gradient, of some function. Let's say Fy represents the height of a particular mountain. The vector g would point downhill no matter where you were. If you're over here, it'd point this way. If you're in this little gully, it'd point down the gully. If you're over here, it'd point here. And of course, the steeper the slope, the larger g would be. So that's what gradient is. Gradient is sort of like the steepness. I like to do a lot of hiking, and certainly I'm familiar with topographic maps. So whenever I go on a hike, I want to see how close are these isolines of same altitude, and the closer they are, that indicates a steeper decline. So going back to the concept of the parallel plate capacitor, when we take a voltage on these plates and we spread the plates apart, the electric field gets very weak because the voltage drops over a very long period of time. As we put the plates closer and closer, okay, let's say they're still 0 and 100 volts apart, we haven't changed the voltage, now the gradient's getting really steep because as we get them closer, the amount that the voltage drops off is much faster. Okay? So, strong electric field when we have a very rapid drop in electric potential, and then weaker electric field as the drop-off becomes less. Okay? Probably not that important for a lot of the things that we do in this chapter. Certainly not so important for a lot of the homework problems and what we're going to do on the test. But this is a really nice application of vector calculus, at least the application of what a gradient means. Now again, going back, here's our parallel plate capacitor, and you can see we set one plate to one voltage, another plate to another voltage, and you can see it dropping off right here. These blue lines, these blue dotted lines, represent areas which are all at the same potential. Okay? So the electric field lines would be in the direction that the voltage is changing. So the next thing that we see with this is that the electric field vectors are always perpendicular to what we call equipotential lines. Okay? I should say, it can be areas, but lines which represent all the same voltage. All right? And again, plate capacitor is really easy for this because with the plate capacitor, we're only dealing with one dimension. In the previous cases, we were dealing with like multi-dimensions here. Now we're only dealing with one dimension, so we're taking the derivative of the voltage as a function of position. And again, you can see 100, 80, 60, 40, 20, 0. Okay? It's dropping, it's getting less, it's going downhill in the positive x direction. Okay? And in fact, the electric field drops off in that particular direction. Okay, what about the case when we have a point charge? What does that look like? Well, now we can actually switch our geometry here and still use a gradient vector, but we're going to say we're going to use a circular, well, I guess it's almost like a cylindrical type geometry here. It's really more of a circular geometry, a radial geometry. And now the electric field is going to point in the radial direction where we put this charge at the center right here. And again, earlier on we saw how V was equal to KEQ over R. So as we got further and further away from this positive charge, the potential will become less and less. Well, what do we see? The electric field lines are pointing away from the positive charge, something that we knew or introduced very early on. Okay? So the electric field is very great, close to the charge, and then the steepness gets less and less as we get further and further away. Again, let's go back to some previous slides from another session. We'll go back and remember when we visualized point charges like this. And again, you notice it's really, really steep close to the charge. That's where our electric field lines are the greatest. And as we get away, the slope becomes less and less, representing less of an electric field. And again, here is a single one. Again, very steep near the charge, drops off by 1 over r squared away from the charge as the steepness gets less and less. So that's another way of visualizing this concept of a gradient. Of course, with a negative charge, the gradient points into the negative charge, and that's where the field lines point.